Welcome to the first talk of this morning session. Our first speaker is Professor Keiji Oguiso from the University of Tokyo, and he is going to talk about symmetries of projective varieties in the view of birational geometry and algebraic dynamics. For the next hour, please welcome.
Thank you very much. Thank you very much for introduction, and thank you very much for invitation this prestigious congress. I'm a bit nervous, but let me start to my talk. And my talk is about this. And in this talk, the aim is something. Some aspect of birational algebraic geometry inspired from algebraic dynamics. And first section, some general introduction, and second section is some application to Calabi-Yau manifold, and third section, some application for real form program. And so let me start my talk. And in this talk, so we are mainly interested in the smooth projective variety. And this talk mostly over C. And F is a dominant rational map. Then algebraic dynamics is interested in the iteration of these maps. And how complicated this map will be. This is main concern in algebraic dynamics. And this program also existence of such F reflect what kind of variety of V. So this is also algebraic geometrical problems. And first measure to measure complexity is probably point is all closed point. So we consider all point after iteration, and if this is very complicated, then we consider this map can be complicated. And which case this can be complicated is, for example, if we take Zariski closure of this, then this covered whole variety, then this is something complicated. But in this notation, I must make one thing sure, because F is just a rational map. So at some point, this will be enter in the indeterminacy locus. In such a case, we cannot continue to make this kind of process. So VF is a locus such that never enter into the indeterminacy locus. Then we can freely make this composition. And then this question is precisely such that is empty set or not. This is first measure of complexity. And later I also introduced two other measure of complexity. One is dynamical degree. This is indeterminacy locus of F. So, thank you. And also, related to this, but more, in some sense, more birational geometric. In my talk, mostly concerned these three measures for complication, and I'll explain this later. So then, to make this non-empty, what is the obvious obstructions or constraint? So if we have this kind of diagram to the positive dimensional varieties, then orbit of this set is enter either in the fiber, most idealistic just fiber, but or indeterminacy of phi. So this set never covered whole part. So if we have this kind of diagram, then it is hopeless to have dense orbit. And the positive dimensional of base is equivalent to saying that invariant function is really greater than this one. Because W is projective. I assume that everything is projective. So if positive dimension, it has rational function, then the composite is rational function from V to P1, and vice versa. And so I'll explain this later. And Zariski dense orbit conjecture is as follows. Roughly saying that this is only the obstruction to have Zariski dense orbit. And actually, this is actually true if base field is C, or more precisely, base field is uncountable field. But if base field is countable field, for example, closure of rational numbers, in such a case, the Zariski dense orbit conjecture is one of the most biggest open problem in arithmetic dynamics. And today, I mostly concerned over C. So this is true, but why this is really true? So the fundamental result is this one. First, Americ Campana, and then Bell, Giosia, Reichstein proved that for any projective varieties and dominant rational self maps, we have some good open dense subset and dominant morphism to projective variety. But in this case, this might be just point, such that orbit of very general fiber is orbit of very general point of this is just fiber of this map. This is constructed by using taking all graphs and take closure in the product of projective space and V, and consider flat locus and make Hilbert scheme to have this kind of morphisms. But here important things is that actually to make this true, we must get rid of countably many union of proper subvarieties. This is already happens for elliptic times elliptic curve. and consider diagonal, and each fiber we have translation by this point. Then torsion point, this is not Zariski dense, but non-torsion point orbit is Zariski dense. So in order to get to Zariski dense orbit in fibers, we need to get rid of countably many points, even if holomorphic case. So this is, but to get rid of countably many proper subvariety, if base field is uncountable, still plenty of many point, dense point. But if we get rid of countably many subset, lower dimension, but if base field is countable, then it could be empty. And because this is not empty, so, oh, sorry. Which direction? This is not empty. So if invariant function field is just K, then this W must be point. So this means almost all fibers are Zariski dense orbit, because this is just a point. Point, then fiber is just whole space. So in this way, we can get this. And another more geometrical obstruction is as follows. In algebraic geometry, we usually consider pluricanonical maps and its image and so on. And this is so-called pluricanonical maps. And the very nice part of pluricanonical map is that because automorphism, birational automorphism preserved by pullback holomorphic n forms never become meromorphic. So all birational automorphism act here. So act biregularly here, but the action is finite. Order is finite. This is the finiteness of pluricanonical representations. So almost for the same reason, because this vibration is preserved under F, and on the base it just acts by finite order. So if we have Zariski dense orbit, then kappa, which is the image dimension of the image of pluricanonical map, must be 0 point, or we don't have this kind of vibration. So this case, Calabi-Yau manifold is one of this case, and Pn rational variety is like this case. So some interesting varieties still remain possibility to have Zariski dense orbit. And actually, I found a bit more precise result. So we consider, so to get Zariski dense orbit, Kodaira dimension must be 0 or minus infinity. If Kodaira dimension is 0 case, the next we consider Albanese map. Albanese map is the next important morphism for algebraic varieties. And in that case, kappa is 0, then Albanese map is surjective fiber space. This is proved by Professor Kawamata, my thesis advisor, long time ago. So, so kappa 0 case, the irregularity must be 0 to D. And kappa minus infinity case, we have unbounded of irregularities. But under the condition, if Zariski dense existence of Zariski dense orbit, then we can prove that kappa must be 0 to D minus 1. The reason is because otherwise image must be general type. If image is general type, then general type automorphism is just finite, as I explained before. So never have Zariski dense orbit. So candidate looks like this, but only this candidate does not occur realized. In this case, never we have Zariski dense orbit. In this case, The Albanese map is a fibration whose fiber is elliptic curve, and special property of elliptic curve predict density of automorphisms. So only a multi-section is possible for orbit. This is a reason. And conversely, we can use suitable elliptic curves and their product and their quotient. All cases, we have examples. And in this way, plenty of cases, we have Zariski dense orbit. And more precise work may be interesting. Anyway, this is first. And next, I'd like to explain a bit about dynamical degrees. This value is really comes from complex dynamics and now useful tool also in birational algebraic geometry. Definition is as follows. Let V be a smooth projective variety of dimension D and choose a very ample divisor H. And consider a rational dominant map from V to V. Then we can define by using H, considering pullback of general piece intersection of hyperplane and pullback, and intersect complementary dimension and intersection of hyperplane. Then we get to numbers, and we consider exponential growth of these numbers. This is called piece dynamical degree. And of course, this is rational map, so definition of pullback is needed, but we can just use resolution of indeterminacy and natural way to define. And this is a non-trivial theorem. Such limit certainly exists. And also, second part is independent of the chosen very ample line bundle or way of resolution. And also very nice part for us is this is birational invariant. So if we have this kind of equivariant diagram where pi is birational, then dynamical degree does not change. And for example, if we have nicely make this is morphism, then dynamical degree is a kind of generalization of entropy, topological entropy, and we can compute dynamical degree by spectral radius of relevant spaces. So this is quite a nice property and also useful in birational geometry. Like this. And it is also interesting that so we consider all possible varieties and all possible rational dominant maps, and then all possible dynamical degree. Then this is looks huge number, but actually this is just countable. For projective case, the reason is because projective variety always defined by finite many coefficient equations, and also rational map is defined also by finitely many coefficient maps, and pullback and intersection is determined only by this information, and limit certainly exists. So just countably many. This is the reason, and for this reason, this part is quite unclear, and I see this is still open. So Kähler case, we take H just Kähler class, then same for all are same. And this is some interesting part, but this is irrelevant to today's talk, so I skip. And arithmetic degree is also interesting things which is over Q, and comparison with dynamical degree and arithmetic degree is still big conjecture. This is so-called Kawaguchi-Silverman conjecture. And this also we don't need it. And if you are interested in this, then there is a good survey of Matsuzawa. So I recommend to take a look. So now we considering primitivity. So Zariski-Dense orbit, we consider this kind of diagrams, and non-existence of this kind of diagram is the Zariski-Dense orbit conjectures part, and this is, but it is also natural to make freedom for this, and F is primitive. No diagram. So this is some kind of irreducibility. So irreducible representation has no such diagram as linear spaces. And this notion is given by Dechi-san. So this is primitive. So no such a diagram, particular implies no such a diagram. So this implies this direction is, and this direction is over C. And I forgot to say that because of the Zariski-Dense orbit conjecture, this condition is birational invariant condition. But it is unclear where, over Q bar, because after modification, we have, it is could be possible to have suddenly have dense orbit. So this is also subtle, but this is Zariski-Dense birational invariant condition comes from this. This is clearly birational invariant conditions. And this is sort of F is only very particular for this given varieties dimension. So never reduced to lower dimension. So this is interesting and introduced, as far as I know, first introduced by Professor Dechi-san in Singapore. And this is an interesting subject. And then I again consider what kind of target is possible. Then this case, as before, first we consider pluricanonical maps. And pluricanonical map must be preserved. So first of all, because primitive implies this one, so kappa must be 0 or minus infinity. And kappa 0 case, next considering Albanese map, then Albanese map must be either birational or just to go to point. Otherwise, we have this kind of diagram. So kappa 0 case, just irregularity is 0, or irregularity is just dimension. And this case is birational to abelian variety for the same result by Professor Kawamata. So compared with previous case, irregularity, the possibility of irregularity is drastically changed. This times this kind of case, but this is only these two. And similarly, kappa is infinity, then just must be point because otherwise the why. Otherwise, the image is not a point, but kappa is minus infinity, so the map cannot be birational. So only this case. And furthermore, we assume minimal model problem and abundance conjecture, but weaker version is okay. Then the case 1 and 2 become more clean pictures. Case 1 is rationally connected variety, only rationally connected manifold. Because we can have maximal rationally connected fibrillation, we can consider if that will be uniruled. And second case is just run MMP, then we can see that this is minimal Calabi-Yau variety. That is Q factorial minimum variety with numerical trivial k. This is equivalent to Q linear equivalent to 0 and irregularity is 0. So Calabi-Yau is really important role in these pictures. So positive irregularity case never happens in this setting. This is introduction, and now honestly speaking, this case is most interesting case, I think, for birational automorphisms or rational dominant map. But I don't have enough result for this, so I stick to this case. And also, this is a conference by Professor Yao, so I'd like to talk more Calabi-Yau. So let's first give some general criterion I found for Calabi-Yau manifold. Minimal Calabi-Yau variety has primitive automorphisms. If V and F satisfy the first condition and second condition, then we conclude that we have a primitive automorphism F. First condition is a condition of the variety itself. So this condition is, we consider all movable effective divisor. And for this, we can make some birational modification to get another possibly different minimum Calabi-Yau variety such that pullback of this divisor become not only movable, but really base point free after some multiple. This is a condition on the variety, and this condition is actually unconditional if we have log MMP and log abundance. But first, log MMP makes D prime F, and then log abundance and F effective. So log abundance makes it semi-ample. And second condition is a condition of F. So characteristic polynomial on this space, Néron-Severi space, is either irreducible over Q or just one additional factor, but this is positive rational numbers. So characteristic polynomial is very close to irreducibility. If we have these two conditions, then F is certainly primitive. This I can prove. And in this assumption, because V prime and V are both numerical trivial K, so this map is just isomorphic in codimension 1. And so the action of Néron-Severi group does not change. So characteristic polynomial does not change. So this condition is invariant under change of birational models. And then can one use this kind of things for studying some concrete example or not? And actually, this part is not yet written down, but I'll write down soon if in this year. And this and this is one application. And considering very general hypersurface of multi-degree 2, in the product of P1, d plus 1 times, and d is greater than or equal to 3. Then V is really d-dimensional strict Calabi-Yau manifold. This means simply connected and no global Holmes until dimension, and on dimension it has unique no fair vanishing global Holmes, which is necessarily up to multiples. So this is very special, looks very special, but studied dynamics for K3 surface case by Vela. So we call this Calabi-Yau manifold of Vela type. Then this Calabi-Yau have primitive birational automorphism always. I proved even dimensional case, odd dimensional case before, but even dimensional case is really new. And to study this, we need to consider first conditions, previous conditions. And first condition of geometry of V comes from these two parts, because that has many degree to maps, and this degree to maps after taking sign factorization, it becomes flops. So using this, we can find birational automorphism clearly. And moreover, this is in that step, we can show that this is unique minimal models. And also by using this Kawamata-Morrison's movable cone conjecture, we can prove. So finally, make after flops, we make all effective movable divisor into neck cones. But in this variety, neck cone is just comes from neck cone of the total space, and all divisors are semi-ample. So this first condition is certainly satisfied. And second condition, we need more, and this is so-called universal Coxeter group. And the if we study the action on the Néron-Severi group, then the action becomes so-called geometric representation of universal Coxeter group. And so this preserve natural quadratic form. And using this, we can show the existence of the map which satisfies second conditions. This part I use some idea already used with Professor Eren and Professor Sun Yu to study lifting of K3 surface automorphism from characteristic P to 0. And in this way, I can find this kind of automorphisms. And also, this is example of Calabi-Yau, but for hyperkähler manifold, we have nice properties that if first dimensional degree is strictly greater than 1, then automatically automorphism is primitive. And first example, as I said, automorphism itself is identity. So we have no chance to have primitive, really automorphism in this. And one interest is, can one find primitive automorphism or not? Automorphism is, for example, automorphism is more better as examples. And actually, using previous result, we can find Calabi-Yau 2n-fold with primitive biregular automorphism for every dimension. And the idea is maybe I think this is interesting, so I just emphasize. So to consider hyperkähler manifold, one of the most typical example is Hilbert scheme of n-point on K3 surface. This is a most typical hyperkähler manifold. And but if we consider NK surface and n-point Hilbert schemes, then it is not hyperkähler, but it is fundamental group is just order 2 groups, and then considering it universal cover, then we get Calabi-Yau manifold. This is strict Calabi-Yau manifold, not hyperkähler. But from universal covering of original NK surface is K3 surface, and Hilbert scheme of D point of K3 surface dominant this varieties. And using this, and if S is very general, then as Professor Kum's lecture, this has plenty of automorphism of positive entropy, and this lift here, and compare the lifting to here, we can find certainly automorphism of this Calabi-Yau 2D fold with primitive automorphisms. And so but this is because starting from surface to make Hilbert scheme, so only even dimensional manifold we can construct in this way. And odd dimensional example, I tried occasionally to find some examples, but never so succeed. And today I'd like to explain why this is some difficult or expect to be very few. So in order to state my speculation theorem, I first recall 2 important rigid Calabi-Yau 3-fold. First Calabi-Yau 3-fold, as far as I know, first found by Professor Beauvue, then Professor Rowan and Professor Yau also make using toric geometry, and then the other person use some applications. So this is considering elliptic curve with period 3rd root of unity, and consider self-product of 3 types. Then we have abelian 3-fold. Then this for each elliptic curve, we have complex multiplication by primitive 3rd root of unity, and then diagonal action. We have Gorenstein action of order 3. Then we have quotient. Then we can take Crepant resolution. In this case, it is quite explicit. So all this has 27 singular point and just blow up. Then we can get Crepant resolution. And this is Calabi-Yau 3-fold. And actually, this is rigid Calabi-Yau 3-fold. And Euler Picard number is 36. And here, one important thing is that this is just Crepant resolution. Usually, it has several ways. But in this case, only unique Crepant resolution. We have only one Crepant resolution. So from here to here, we are uniquely recovered. But in general, contraction has many possibilities. But from here to here, this is also characterized as maximal C2 contraction. So this means pullback from downstairs non-severity with intersection of C2 is always 0. And this is maximal one. So from here to here, we can uniquely recover. So automorphism here, also automorphism here. In this way, we can compare automorphism. So similarly, let us consider Jacobian variety of Klein-quadratic curve. Then that curve has natural automorphism of order 7, which gives Jacobian automorphisms of the same form, and then again Crepant resolution. And this case also, this is unique Crepant resolutions, and at the same time unique birational C2 contractions up to isomorphs. And in both cases, using this property, I can compute automorphism group precisely. And among them, I can find many primitive automorphisms. Many primitive automorphisms. And so far, we get two examples. But these are all quotient of abelian variety. And I suspect that actually these two are only possible examples. And I'd like to explain why I suspect this kind of thing. First of all, I recall important theorem, important role of second Chern class of Calabi-Yau threefold. This is, first of all, second Chern class is strictly positive on the ample cone. This is because V is strictly Calabi-Yau, and this part, I think, only Professor Yau's result can be applied. Because Professor Miyaoka says that this is pseudo-effective and equal to 0, then it is étale quotient of abelian variety. This is not really followed. So anyway, Professor Yau and Professor Miyaoka's result, C2 is positive on ample cone, hence non-negative on the Neff cone. So if looks like either looks like this, and it is not so difficult, but if automorphism group is really infinite, then Professor Wilson's old result shows that figure of Neff cone and C2 hyperplane is not of this figure, but just touched at some point, just non-zero point, touched at non-zero point. And actually, finally, I show that this is first two examples only two birational contraction, C2 birational contraction of strict Calabi-Yau. And so this is known result. And there is a question. First question is rationality questions. So if automorphism group is infinite, then there is some real point, at least real point, there are intersection point. But so far, example I know all has Q rational intersection point. And actually, I can prove if F is zero entropy, then actually that is Q point we have. So I wonder if automorphism is really infinite, then whether or not we have really rational intersection one. This I call rationality question. And second question is for all Neff divisors, but not zero, on strict Calabi-Yau, then some multiple becomes really effective. Once we show effectivity, then by log abundance or my old result, some multiple becomes semi-ample and we have fiber space. So second question is somehow people expect, but very difficult and very notorious questions. So far, only partial answers. And one speculation is that if both these two both are affirmative, then strict Calabi-Yau threefold, which has either Zariski dense orbit or primitive automorphisms, then it is necessary one of the two examples I give previous. So this somehow explains some difficulty. And another thing is that if first part is true, as I said, if second part is affirmative, then so all point the Zariski closure is for space. Such a automorphism is called wild automorphisms. And then Calabian threefold having wild automorphism does not exist. This follows. And then this implies existence of wild automorphism implies only abelian varieties in dimension 3. This is also conjecture. And so I think it is interesting to prove this without any this kind of assumption or just disprove. So find new examples. I cannot succeed, but then it's very interesting, at least for me. And of course, if this disproved by chance, then I think first statement has some does not satisfy. If second statement does not satisfy, then it is very, very, very remarkable will be result. 10? はい。10 minutes. Still 10 minutes. Thank you. This is some application and speculation for Calabian case. So this explains some difficulty, but it is still interesting to find Calabian threefold with interesting biregular automorphisms. Birational automorphisms we have plenty of, as I explained. And finally, I'd like to go some indirect application. And this is so-called real form problem. And we consider complex variety V. So this time structure morphism is important, so I wrote. And then real algebraic variety, so scheme over spectra is called real form if base change to C is isomorphic to original V over C. In that case, we call this is real form. For example, if equation of V is all rational coefficient, then that is real form, already real form. And if we have this diagram, then identity of W times complex conjugation of spec C. This is involution of V, and dividing out V by this involution, then we recover W. Note that this is complex conjugate, so the structure morphism does not preserve, just base also go to conjugate. So we recover this. In this way, real form and real structure is equivalent notion. And also, I don't explain much, but this kind of real structure is naturally translated, naturally I translated into the Galois cohomology. This is, and question is, main question is, the last destination is describe real form for each given varieties and to find some unexpected real form, then it is interesting. And second question is more conceptual. Real form is always finite or not. So there are finitely many ways to describe rational coefficient, real coefficient variety or not. If otherwise, what kind of variety has infinite real forms? This is interesting questions. And for example, Fermat case, almost all Fermat real form is described by my student. That is quite plausible. And but most surprising recent result, not recent, is this Regiutora's result. He find smooth projective complex uniruled but not rationally collected variety of dimension 6, which has infinitely many real forms. And this is my first motivation, and I study this program with several co-authors, like Dean. He's complex dynamic people, and also Professor Sun Yu. He's algebraic geometer and here, and also later Gashet and Hoshyu Lin, and also my previous PhD student and now in Professor Yao's center in Shanghai. Fortunately, he got a job. And 6 authors. Finally, we generalize this and some satisfactory answer for at least as first stage. Maybe I first show this. This I already explained. And first result is, as I explained later, if dimension 1 curve case real form is just always finite. So interesting case is up to dimension 2. And in dimension 2, we found the first restriction. If surface has infinitely many real forms, then this is either isomorphic to rational surface, or this is, I think, interesting, non-minimal K3 surface, or non-minimal N case. Birational geometry usually always goes to birational models and consider invariant property under birational modifications. But this suggests some delicate difference between birational modifications. And actually, we show that the converse is also true, that there exists some complex surface, which is just one point blow up of projective minimal K3 surface. But the minimal K3 surface is not here, so only finitely many real form. But just one point blow up makes real form infinitely many. This is something drastically change. This is, at least for me, it is quite interesting. And also, NK surface same. It's just one point blow up. Technically more difficult, but doable once we get this. And also, this is the most difficult case, I think, but the rational case also we find rational surface with infinite real forms. So surface case, we can find somehow where somehow necessary and sufficient kind of result. So this is all certainly exceptions. And of course, it is interesting that what kind of minimal surface or what kind of minimal NK surface has certainly infinitely many real forms. So such characterization is probably next step, but this we don't yet know. And one of the interesting part is for this proof, we use some complex dynamical property such that if automorphism is zero entropy, then we can show that the real form is just finite. So, for example, elliptic surface of codile dimension 1, it has always structure morphism to curves whose fiber is elliptic curve. And in this case, the fibration is preserved by automorphisms. And from this, we have dynamical degree 1. And this implies elliptic surface of kappa 1 never has infinite many real forms like this. So this is useful. And second one is very roughly saying, if variety satisfies Kawamata-Morrison conjecture, finish, then we have finite many linear forms. So K3 surface, abelian surface, entity surface, and so on are all excluded. And finally, in all dimensions, we have rational variety with infinitely many real forms and some constraint for existence of real forms, infinite real forms, and converse. This is all. Thank you very much.
Thank you, Professor, for this beautiful talk. Any questions? Okay. Yeah.
So you talked about this word type color BL completely intersection of 222 in P1.
Yes.
So does this color BL of word type has modular space? Has modular space?
Yes. Because coefficient changes.
Okay. So when you change it, it has.
Yes, but for all general one, general one means if not general, then automorphism group is always finite, but not identity. I just avoid this case. But
okay.
This case,
so this is different from smooth one. General is more strict than small.
General is really in the sense of general, Zariski dense in the Hilbert scheme.
Okay.
Yeah, not generic.
More questions?
Professor, I have a basic questions. Why the DPF you define is an algebraic number? Why the DPF you define? You mentioned it is algebraic number.
This is expect to be algebraic numbers, but currently there is counterexample is found. Number is just countably many, but nevertheless this can be a transcendental number. This is proved by 3 authors. Where? That is rational variety, and their construction is just for first dynamical degree.
I'm just asking if you said it's a transcendental number.
Yes.
But is the transcendental number a period in the sense of Zagier?
That is defined just by how to say Laurent polynomial solutions, and not explicit. For example, we don't know if pi or e can be dynamical degree or not. This is
Okay.
More questions? I have one somewhere, but I don't remember where. You defined the veil height up to a bounded function. In a previous slide, you defined a height, the veil height up to a bounded function. And I would like to know, how do you use them to prove these theorems? Or
which one? Height. I don't use any height in this talk.
Oh, sorry. I thought.
This is this
Yes,
talk is
here.
some relation to the dynamical degree. And
Yeah.
if I have a time, then I try to explain. But this is irrelevant. But
Okay, but you don't use them
in my motivation, for example, first theorem like this kind of this theorem is also true over Q bar. And first, we want to understand Kawaguchi-Silverman's conjecture, also Zariski length orbit for over Q bar. We find this. So the Kawaguchi-Silverman conjecture really motivated. And what we proved is that for threefold case, if it is irregular, then Kawaguchi-Silverman hold for birational automorphism, not biregular. This is one byproduct of.
Thank you. And I have a last, but it's a very naive question. Because at the beginning, you said that K is algebraically closed and of characteristic 0. So can you apply all these results for CP, the p-adic complex field?
Complex?
The p-adic complex field, CP.
I never consider.
Okay.
You may consider. And probably many part is for example, construction of Calabi-Yau. I don't use it.
Okay.
And threefold example also we can write down more algebraic. So this could be possible.
Okay.
But maybe cohomology should be changed from Betch cohomology to other cohomology.
Okay, thank you. More questions? Okay, we can applaud the speaker again.
Thank you very much.